Hi everyone. I realized before the break that I thought this was the end of a lecture, but we still want to talk about standard forward, so this is going to be two-part recording. Whoops. Um, However, we're just going to chat about this quite briefly, and then we're going to jump into um, assignment 3. In fact, I might just put this as the assignment 3 recording and say to whoever's watching this, skip the first 10 minutes of this video and go straight to assignment 3. Might be the easiest thing. I think the first thing to preface with the standard forward topic is that standard forward is not accessible in this course. The sad reality of COVID is that all of your exams now are basically open book, which I think is great for some courses and is kind of good for this course, but you know, it makes it really hard to ask theoretical questions anymore. And test your knowledge because everything's Googleable. Now that's not a bad thing. I'm a big fan of if you can Google it, what's the point of expecting you to know it? Though it does mean that your exams are mostly going to be practical. Your exam will be practical, so standard forward doesn't really appear much in that exam, and it's not really required for assignment 3. But let's just kind of quickly take a look through the steps that lead us to this magical function called standard forward or forwarding functions. The thing about forwarding functions, I'm just looking whether we want to talk about that or not, is that, remember how we said because of reference collapsing before that and because of binding, what actually often happens is that when you do something such as, this, you can sometimes lose a particular property of a type. So goo in this scenario might be an R-value reference, but once we pass it into this function, at this point here, when we're printing out A behaves like a const L-value reference. The fact that it was an R-value reference previously is kind of lost by the binding. So sometimes what we want to do is we want to be able to forward or retain that particular, how that type is without losing it. So we're basically going to go through some steps here. It's like, if you have a templated function called a wrapper that takes in a type t value, and then what it does is it returns the result of calling another function. All that's going to happen is things are just going to be copyable, or if you try and pass in a type that's not copyable, then this is just like your standard copy case. We don't need to kind of dwell on that too much. We've learned that a more robust way to define some kind of function is with something like a reference to a const t or a const L value reference, and this is kind of okay, and it mostly works. Though the only problem is that it doesn't work in scenarios where we want to pass in an R value reference that is non-const, and we want it to be modifiable. Because in the previous examples here, while something like this did work, it doesn't work for times when we actually need to modify A. It only works for times when we want to deal with it as like a const because it is const. So the something like this, while it does pretty much allow most things to bind to it, it leads us to a problem where if we try and pass in a non-const, or in this case an R value reference, you just can't modify it because it gets binded to an L value reference in this case. Other ways we can look at things like we've seen before is that you could just use a reference to t, just like a TL value reference. This allows things to be modified, so we're kind of just recapping what we learned previously. Though the problem with this is that now what happens is that we can't pass const things into it. It's the problem we saw before. So sure, it's mutable. Sure, it can take in. Can it take in R values? I don't remember. But now it doesn't. So if we pass in a const object, we're going to have a problem. If we try and take a constant n and we pass in there, we're going to have a problem. And I think it doesn't really work well for R values either. This is another thing I thought we cut out of the course, but we didn't. Sorry. I always forget this when I'm prepping it because I delete lots of slides and then I forget it every time. So we talked about reference collapsing before, and how there are lots of different cases where pretty much an R-value reference of an R-value reference collapses into an R-value reference, but all other kinds of things end up collapsing into an L-value reference, which, you know, is kind of semi-interesting and semi-boring, though the relevance of that is that we need to think about this when we are calling certain functions. So what did we say in the previous slide? We looked at the binding examples and we said, you know what, both a reference to a const t and a reference to a templated t, everything can bind to it. The good thing about a reference to a templated t, though, is that it's non-const in these cases. So if we created a templated function like this, template type name t auto wrapper takes in a templated R value reference of a value, and then it calls function on that value. In the left hand side here, how this will work is that if I had an int I and I called wrapper with that int I, if I called this function, how is the template instantiation going to work? Well, it's going to create two instantiation, well, it's going to create one instantiation for me here, which is that it'll create a, you know, an explicit, like, well, you know, an instantiation is like an explicit specialization, essentially, right? It's saying that we have a template type, let's create an instance of that function. And all it does is it replaces that t here, right, with the type, which is a L value reference. Now that's the case because when we're dealing with all these reference types, just a standard old variable is an L value reference. You know this, like if you just declare an int I and you pass it into a function that's expecting a reference, it just takes it by reference. And it replaces the t in this function here with an int reference. Now the reason we care about reference collapsing rules is because this will tell us what kind of type it is, which in this case collapses to a L value reference, right? Because the R value reference of an L value reference is itself just an L value reference. So basically, this is kind of like roughly what it collapses to here. And then on the other side, if we created it in I and then we passed into wrapper an R value reference, a non-const R value reference, right? And I think I've just... yes, okay. Nathaniel's spotted that too. So it's like... Yeah, so this one is a little bit weird, but essentially, I mean, the same thing can be taken away from it. I think the only thing here is that this t, like standard move, doesn't actually, like while it makes it an R value reference in the literal sense of what happens here, it's actually just an int. But forgetting that for a moment, because this is just a little bit more demonstrative, is like, this is just another example of how reference collapsing might work from a compiler level, in terms of a compiler will get you know, it'll try and instantiate a particular templated function like this. It'll put in the values if it can. In this case it's an int, but if you assume that it's like an int R value reference, then it does collapse into something like this, and then you're left with these two kinds of functions. So if this was the case here, and I mean it still collapses to the same thing, well, it doesn't collapse, but it still ends up at the same, nearly the same thing. This is an example of how, like, if you have a wrapper function like this and you call it with two different types, you're going to get two different instantiations depending on that. Now, where things get weird is that just moving on here. So if we want to generate something like this, right, auto wrapper L value reference, it takes in an L value reference, and then we cast, before we take into this function, another L value reference, and on the other side we do the opposite for R value reference. The reason we might want something like this, where for R value references we force the value to be passed in as an R value reference, and for this one we force it as an L value reference, is to essentially preserve the reference type. Because the reason this example kind of has a wrapper and a function is because essentially, because of reference collapsing and binding and stuff, as you're passing things through and they bind, you can sometimes lose the information associated with it. And that is why we have this mystical function, which I don't know, is standard forward? Is it a built-in? I can't remember if it's what library it's part of. Utility, is it? Yeah, it's defined in utility. And what standard forward essentially does is standard forward tries to preserve the specific reference meaning in terms of here we have our wrapper that is a templated T R value reference, and it takes in that templated R value reference type. Though by putting standard forward around the value we're passing in, like we're kind of calling that underlying function, this here, all this really does for us is ensures that in cases where this collapses or just turns into an L value reference, that we make sure we're calling function with an L value reference, and in this case here it makes sure we're calling it with an R value reference. So essentially what this is saying is that if you have standard forward in a function, if an instantiation of this templated function wrapper instantiates with an L value reference, then standard forward will make sure that whatever you're passing to function is static casted as that, and if it's an R value reference, it's static casted as that. It's essentially ensuring that like L value references are transferred through, and the same for R value references. Now again, let me just see how many more we got. Yeah, so generally speaking, this is mostly useful in scenarios where you're writing like a generic function that takes in like an R value reference to a template where you don't really know how it's going to get used, or in this case here, you're like, look at this, like MakeUnique, right? So we're doing a little like mini case study on like a simplification of MakeUnique. And MakeUnique is just to say a function, and it's using variadic templates, which we talked about last night, to take in a number of arguments, which makes sense, right? Because if you think about MakeUnique as a function, you can say MakeUnique on standard vector of int, and then you can just give it like 1, 2, 3, 4, 5, and suddenly it just takes in any number of arguments, and that's because it's using the variadic template stuff. So it can take in any number of arguments, but to make sure that it can take in R values, L values, const L values, etc., we not only use the variadic templates, but we also use the R value references of a templated type here, which ensures that everything can bind to it. The return type of MakeUnique is obviously a standard unique pointer of type T. That makes sense because MakeUnique returns a unique pointer. But you can see here, like, and this is a simplification again, MakeUnique will actually return a new unique pointer where it will do the new for us. It'll memory allocate that for us, a type T, but we use standard forward here to make sure that all of the L value references or R value references of these args are preserved, because there's the chance that a particular instantiation of MakeUnique, depending on whether it generates certain args as L values or R values, might, restrict us and lose that particular, I don't know what to call, like the L value referenceness, the referenceness of a particular type. So again, this stuff is very academic in the sense that we're going into quite a lot of weeds here and quite particular use cases that most of you wouldn't have really come across, and a lot of it is mainly relevant when you're trying to deal with situations where you're working with L values and R values, though again, it's not something we're assessing, so please don't stress out if your value category is a technical term. I like referenceness. What are some uses of standard forward? Well, the really specific use of standard forward is when you want to wrap a function with a parameterized type. So let's say you're creating a function like MakeUnique or MakeShared, but it's a templated function, and it's really just when you are because the thing is, templated functions tend to operate or themselves call functions that you don't understand or have context of. Like, the key thing to notice here is that we're creating a new T, but you don't know what T is. You don't know if T is expecting L values or R values. You don't know if it matters. So by using standard forward, it's kind of like, I guess the way I think about it in my head is like you're trying to create like a true middleman, for lack of a better phrase, that can, it's templated enough to be called in a range of scenarios, and you're just passing stuff through. It's not opinionated. It's not trying to say that we're going to collapse this or do this. It's just like, I want to try and preserve a lot of the original meaning and value category of our types as much as possible. And again, like full disclosure, generally anytime I refer to a topic as academic, what that means is that I understand it because I've read about it and studied it and poked around with it or taught it, but I've never really come across a scenario personally, and I'm not a daily C++ programmer where I'm like, oh, cool, I really need something like that. But I hope that gives some context on what Standard Forward is. I mean, if you want more information, you can obviously just Google Standard Forward and read about it. Because there's a lot of information in CPP reference, and there'd be a whole bunch of other examples online. Though generally speaking, this is one of those things where you're very unlikely to run into a scenario where you're like, do I need to use Standard Forward here? Like, if you aren't sure you need to use it, then the answer is probably no. Like, it's not something that's going to creep up on you like smart pointers, where things you were doing before without smart pointers you should now do with smart pointers, or anything like that. But there's some context to keep it in mind. That's technically the end of this lecture. I will actually stop the recording and start another recording. Mainly just, I was thinking as I was talking that that's probably better. So if you could leave feedback on... this is just the advanced types lecture. That would be really great. Thank you. I would really appreciate that. See how you're all feeling about it. See what we got to change for next year, potentially. And then we'll get on to assignment 3. Just seeing how many people have filled it in. I've had one person filled it in. Someone says a lot of ampersands. So if you're sitting there, if you're lying on your bed, if you're sitting on the toilet, if you're making dinner right now, I don't mind. Just grab your phone out, snap it. Takes all of a moment just to give it a general feel for what you thought was interesting. I mean, the general, if you do fill this out, I mean, this is the same for people watching the recording. The main thing I'm interested in is like how much you find these... Do you find these topics interesting even if you feel like they won't have an immediate practical benefit to you a lot of the time? You know, like, are you like, this is just really interesting to think about the language? That's kind of the thing I'm most interested in. Anyway, thank you.